Welcome to Office Hours. It's November 22nd. Let me actually make sure that all of this is properly configured. Okay, that doesn't work. That's the only one that doesn't work. Never a dull moment with OBS. Never a dull moment. There we go. Okay, now let's open up the chat. Okay. My graphics drivers are now fine-tuned for this office hours. Yes. Every time anything gets upgraded. All right. What do we got? Wow, let me announce that we are live. All right, I don't have much time, but I have some time, and we can go through some interesting concepts if you are interested. All right, let's roll. Can we talk about 10 and by extension 9? Sure, let's talk about 9 and by extension 10. I'm eating some cottage cheese and jam. All right. So let's grab level 9 off the website and go from there. Let's go to the dojo. Challenges. Start in on level 9. Hit up in practice mode. And then let's oh yeah, I just rebooted. All right. Let's copy the challenge over and open it up in IDA to see what it does. Kernel level 9. All right, so let's take a look. What does this challenge do? Well, it has an open, write, and release. Init does nothing. Cleanup does nothing. What? Why? Okay, no, here we go. Okay. Init creates a pwn.college device. Cleanup removes it. Then there's some padding so that everyone has different offsets. Release does nothing. Open does nothing. All the relevant stuff is in write. All right, so what do we have? Is this level 9? Doesn't feel like level 9. No, it is level 9. Okay. All right. So we have a logger structure that has some size. And what the hell is this? This is some IDA insanity. That's interesting. Can we just tell it to... Okay, let's change the type. Okay, that's a real weird type here. Did it create that automatically as a local type? That's insane for some reason. local types. Maybe. Oh, it must have matched it to some internal type in its type library. Insane. All right, so let's make this thing a char buffer and see what happens. It doesn't like that. Okay, it doesn't like. Hold on, let's see what the argument to memset is. It is, where's my memset? Ah, this is the memset. Should be in RCX. That should be the memset. Is this the only? No, it's not the only. Okay, it should be 108 bytes here, right? What the hell? Sorry, this is really interesting in that it created a type automatically, and then it named it something absurd, and now it's very hard to interact with. All right, E0E with the $sign. E0E. Not here at all. Huh, interesting. Interesting. Ah, here we go. Oh, I see. It's called device write E0E. So let's change its name to cool struct. Okay, that's going to be a lot nicer to look at in the pseudocode. Now it's a cool struct, and cool struct has a log function, and cool struct also has and that log function is initialized to print k. And cool struct calls copy from user, which actually takes 3 keywords: source, destination, and length. Boom. And it copies in the length. Okay. So it seems to me that we write in a structure to this device file. And the structure that we write in basically is gets written into logger, and the structure, so since we write it directly to logger, let's just say that this structure is not just a character. This structure is actually a cool struct pointer, just in user space. So we create a cool struct pointer in user space. We write it to we write it to the device, and it checks to make sure that the length that we're writing isn't too great. If it's too great, the kernel dies. If it's not too great, we basically write it into this logger struct in the kernel space, and then we call the log function. So this is a log device. So let's try to interact with it dynamically and see what happens. All right. Boom. So my keyboard is not responding anymore. Oh no. Okay, there we go. I accidentally locked the keyboard in my little sub X terminal. Okay, anyways. So let's SSH in and see what's going on. VM connect. So as a reminder, what we need to do is send in some bytes that will represent a logger struct. Actually, what we didn't get to is what the hell is a logger struct, because IDA identified it for us automatically, and then no, that's not what we want. And then we just kind of went with it. All right, let's expand this. So a logger struct has a buffer that seems to be 256 bytes long and a log function. Let's actually make this, what? Oh my God. IDA's 2 levels of types are really annoying. Where's our cool struct here? Cool struct, thank you. No, we don't want to double click on that. We want to right click, say edit, edit, edit. Where's edit? Edit, yes. Okay, so we can, okay, no, it has the, all right, so it's a char, boom, okay, never mind, all is good. So it's 256 bytes, and then the function pointer, all right? And interestingly, this is checking for a size of 264 bytes, not 256 bytes. So this is using size of logger instead of size of logger.buffer, right? That's a pretty bad problem, because if we are able to write that entire struct, then hey, you also have this print k. All right, so let's just make sure that we can log something. Let's do VM connect. Oh, I already did. Over here, let's connect in VM logs. All right, here's our VM. Awesome. This is our module logging that we're good to go. Let's write. So, okay, again, we need to write some amount, and then let's go back to the terminal. All right, so here's the logs. Boom. We echo hi to pwn.college. We log hi. There's some weird bug where VM logs will log everything, will read everything from the log twice. Connor's on it. It will get fixed. Hold on, he's DMing me. Okay, anyways. I'll see what Connor means later. Is he on here? Oh, he is. Connor, I don't understand the significance of what you were telling me, but I'm sure we'll run into it when I actually look at that. Okay, anyways. So we write data and we end up here. Okay, so that's great. Now let's do one more thing. And we do VM debug. Actually, first, tail proc kalsims. Let's get our right handler. It's going to be right there. I'm going to VM debug. We're going to break at the right handler. We'll hit continue. All right. Let's do this. Echo hi. We'll write hi in again. Here we go. We have now braked at the right handler, and if you recall, we have a bunch of arguments. RDI will contain our file structure pointer. That's fine. We don't really care about that. Our SI will contain our buffer. Our DX will contain our length, and our CX will contain the offset of our that we're writing into the file. This isn't used anywhere here. That's fine, but the length and the buffer are used. Okay, so let's take a look. RDI, that's a pointer to our file structure, representing the open file that that Echo, or really Bash, has opened into pwn.college. Our SI, this is the user space structure with the data in it. If we do access, there it is. Hi, right from user space. This is from Bash's user space, right? It's because Echo is a Bash built-in, or at least the version of Echo we're using right now. So somewhere in Bash, it created a string in memory and put hi in it, and it's writing that out to file descriptor probably 3, which is, well, maybe not, which is its open pwn.college module. Okay, then our dx is the length 3 h I new line. Our cx is going to be 0. Oh, no. Our cx is a pointer to the structure where there is the offset, which is 0 right now. Dot offset into the file. Cool. And that is how this function was called. Awesome. So where does that leave us? Well, where that leaves us is two things. One, and let's just take a look. Let's disable this breakpoint. If we create a cyclic pattern of 300 bytes, this will definitely overflow, that buffer, and it'll also definitely be caught by this check right here that the length is not too long. Okay, what's going on? Why can't I generate a cyclic pattern? Oh, I'm inside the VM. Okay, yes. Inside the VM, the cyclic pattern is not good. All right, let's detach. Sorry, pwn tools is a little slow inside, or it doesn't work for me at all actually inside the VM. I don't know if other people have had that experience. Okay, so here's our 300 byte cyclic pattern. We're just going to cat it into pwn.college. We have the logs right here. And interestingly, we have a buffer overflow. Oh, yeah. Okay. I was like, what is logging that? And here's the line that says buffer overflow detected. And saying the size that it'll accept is this. The size we sent is 300, because that file was 300 sized. And that's it. You're done. But the kernel actually doesn't crash. I thought bug made the kernel panic, but I guess that's panic. Anyways, just that system call failed with a write error. Said no space left on device. That's interesting. I wonder why that happened. But I guess that's some yeah, that's interesting. I'm not really sure why cat assumed that it failed because of no space left on the device, but that's where we are. So now what? Well, a couple of things. One, we know that the buffer in this structure, if we go to local types and look at the definition, that buffer is 256 bytes long, and after that there's an 8-byte function pointer. And here, this uses the size of that entire structure to check the length, so it'll allow you to write 264 bytes, which means you can start clobbering the function pointer. All right, let's take a look at what happens then. So we're going to now create a 264 byte long cyclic pattern. And because we actually want to query it, let's make it an 8 byte at a time cyclic pattern. And let's send it into that kernel. and sec fault. So let's see what happened. So what happened, first of all? If we strace this cat, when it did the write sec faulted. The write syscall sec faulted, which is insane. Syscalls aren't supposed to sec fault, right? Syscalls are supposed to return with an error message if you do something wrong. A syscall should never sec fault you unless you're calling kill on yourself with the signal. Even then, no, then kill won't return. Yeah. So, but here you did a write to a valid file descriptor, and you result in a sec fault. Well, what happened was that the kernel thread processing that syscall sec faulted, and that just got propagated to your user space process. And if you ask yourself, why did we sec fault? We sec faulted because we have a bad RIP value. Actually, let's take a look at this. We have a bad RIP value. What was that RIP value? RIP got set to this. Let's take a look in the cyclic pattern. That is exactly 256 bytes into the cyclic pattern. And that is where that got overwritten into RIP. Or that got loaded into command control flow, got diverted into that data, the data from our cyclic pattern. Why is that? Well, that is because when we did this copy from user and we did a copy of 264 bytes, we overflowed the 256 bytes in the logger, in the actual buffer, plus the 8 bytes of the what's it called? I just had a very interesting... Okay, sorry. Plus the 8 bytes of the function pointer. Connor, I'm going to send you a message right now. Okay. Anyways, all right. So we overwrote the entire logger structure, which includes a function pointer, and that function pointer is this log function pointer, and it's called right away. So our random data that we put in is called. All right. So what might we do? Well, you might say, okay, first things first, let's right away try to call our buffer, like the buffer that's inside logger. Let's try to call it as shellcode. Right? Well, of course that won't work. This buffer is on the stack, on the kernel stack, and that kernel stack is going to be have non-executable data, right? So we have NX. So now we're kind of screwed, right? So we can't redirect log function into our shellcode, even without KASLR. Without KASLR, we probably know where our this logger will be. So we have to figure out what to do. And the answer to this is in the lectures, right? So we can call one function and we can control the parameters to it, right? And with that, we should be able to get the flag, or at least make the flag gettable. All right. Let me show you an example of calling some other function. I'm not going to give away the answer, but I will. Let's see, what can we do? Where can we redirect execution? We can call something else, something interesting, such as this buffer overflow detector. You see how this is super cool and it prints the text bold as opposed everything prints in bold. Even our highs print in bold? Yeah, it prints bold. Well, I wonder what the difference between warn PK, print K and just print K is. All right. What can we call in the kernel? That would be very cool. I mean, first, let's just make sure we can overflow it with the address of print K, right? How do we get the address of print K? Well, we can read out in this VM. We can read out the K all sims, and here it is. This is the address of print K. If we make a cyclic pattern of 256 bytes plus, okay, here we go. So that plus, and this won't pwn. Does pwn have the pack and unpack? No. Why wouldn't they have it? Why just hex and unhex? This is so annoying. Okay, and then this address, E9 52 0B 81 FF 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 FF. Okay, and we actually want to unhex it. Okay, here's our attack. Our cyclic pattern of 256 bytes, and then the print K address. Right, the address of the print K kernel function. This should now print successfully again. And it does. Just took a little while. And it prints out our and it prints out the string that we logged. And if you notice something, it prints something else too. So, what did it print? It printed E9 capital R, which is 52. Oh, here, let's just go. Where's why is there a \x? What the fuck? Why is this? Okay, so here's our crazy our cyclic pattern. What the hell is that? I mean, I know what it is, but why isn't it just nice and clean? E952OB, why is it in hex? I guess it automatically escapes it all in hex. That's crazy. Print K is weird. Yeah, maybe print K is fancy. All right. You can kind of see here, even though it partially translated into strings for some strange reason, which I don't understand. What is this? This E9 \x E9 is E9, the least significant byte. 52 0B 0B \81 81 and so on. All right, that is the kernel printing out to you the address of print K. Why does that happen? Because the kernel is written in C. It operates on C concepts such as C strings that are null terminated, and you just overwrote the null byte at the end of this logger buffer. And so when it did print k, you managed to read past the buffer, output past the buffer, and log the address, right? Now this has very obvious implications for level 10, because obviously that is level 10 is this, but with ASLR where you don't know where the kernel is. Awesome. All right. Hopefully that was helpful without giving away the answer completely. Of course, I didn't actually carry out the attack, but what I did do was trigger the overflow, attain control of the function pointer, and even use that same overflow to leak that function pointer back out. In that case, I knew the function pointer, but let's just do it to drive the point home. Do it one time where we don't know the function pointer. We have a C256 file. Let's just reboot the VM. Oops, we don't need hex dump here. Okay, come on. Come on. Okay, perfect. All right. So let's CAD this into pwn.college. Twice. Okay, there it is. You see it right here. Oh, Connor, it's your fancy print stuff that translates it. Interesting. dmessage or whatever is generating the colored output translates it. The other one does not. Here it is. Here's that unadulterated address. All right. So we didn't overwrite. We did not overwrite print k or the function pointer this time. The log function pointer of the logger structure. What we did do was just overwrite the null terminator of the buffer right before it and output the address. This is that same address we know and love and remember, right? It's our the address of print k in our kernel. But what if we were running with ASLR? Well, let's try it. Level 10 is level 9 with ASLR enabled. Let's start it up. Practice mode. All right. Let's VM connect. Okay, we're in the VM. It's VM logs from the outside. Or, by the way, dmessage from the inside, right? And do this attack. Print k, I guess waits for a new line to flush. There we go, okay. Here's our outputs. Looks kind of similar. You still see that capital R. And that makes sense. You remember with ASLR, even when things are moved around, they are moved around being based on a page address. And here again, we have E9, 52. Wait. 0B81FFFFF. KASLR is still off, but we're on level 10. Oh, it's off in practice mode. Is that the case, Connor? Connor, you're killing me. You know what would be good? What would be good is if we change the VM script to have an option where we could force KASLR. Yeah, that would be good. All right, I'm going to force KASLR manually. Okay, this should work. Okay. But where does this check for? Ah, okay, okay, here, this way. Okay, okay, okay. Here, fuck it. We'll just say, oh my God. Oh, I'm not root, that's why, okay. All right. Okay, so now when I reset the VM, we'll have KASLR. Okay. Can we see, are there any addresses in the demessage logs in general? There shouldn't be, right? No, there are ranges. Just seeing if we could cheese this. I don't think so. Okay, cool. All right, so we're booted up, VM Connect. Let's do our attack, overriding the buffer and the null byte at the end. Boom. Okay, here we go. Hex dump. All right, our address is, drum roll. Let's find, okay, here we go, 610. E952, that's familiar. 6BBB, not 8209 or whatever it was. 6BBB. So ASLR is now on, but by overflowing the null terminating byte of the buffer in this logging structure, we trick the kernel into printing it out to us, into printing out the address of log function, because that's the next thing in that structure. Remember, the kernel is just a bunch of shitty C code, just like everything else, or most other things. And so it's vulnerable to the same shitty C vulnerabilities. If kernel developers aren't extremely careful, you end up with overwritten null terminators, or even format strings, or things along those lines. All right. Did that help for 9 and 10? Now, what do you do, of course, when you leak the address of printk? Well, using the address of printk, just like when you're attacking user space ASLR, you can calculate the address of any other command. So, or any other function, sorry, in the kernel. So if you got printk, let's scrap it a little more carefully. Okay, and you were interested in calling prepare cred. That's not the right way to solve this, by the way, but if you were, prepare kernel cred, you could take printk, the address of printk, subtract the address of prepare kernel cred, and you have a constant offset, and then you can calculate that when you leak that address. Oh, oops, lol. There. Now, what is the... what am I trying to say? As I mentioned in the mitigation lecture, there's an emerging, upcoming new kernel security mitigation called function granular KASLR, FGKASLR. That means that the functions themselves will be shuffled around. So that won't necessarily work. If you just leak one address, it won't necessarily tell you everything you need to know, but it'll likely tell you some amount of useful information that you can then use to go onwards. Awesome. All right. I have time for another really quick question. If we have someone has a question that we can cover. Actually, I wanted to give a hint on level 12. In level 11, of course, you have to pull the flag out of someone else's memory, right? And that's perfectly fine. You can do it. I believe in you. In level 12, flag files are erased. The process that did that dies. What happens to physical memory when a process dies? Or what happens to a process's memory when it dies? When a process terminates, all of its memory is returned back to the kernel from whence it came. The kernel decides what to do with that memory then. And different kernels differ, and different configurations and different system conditions will cause the kernel to do different things. So the typical thing that a kernel does with memory that's freshly returned from a terminating process is nothing. Similar to a heap allocation. You keep it around for the next time someone asks for it. Of course, if one process terminated and another process launched up and asked for some memory and you gave it recycled memory pages with data in them, that's a very clear, serious security vulnerability. And that's why that doesn't happen. Before handing it memory back to another process, the kernel clears that page of memory. But only when it's about to hand it back to another process. Until then, it doesn't make any sense to spend the runtime to pay the performance cost to overwrite an entire page of memory with zeros. So all that data is still there, chilling in memory, waiting to be reused by the kernel. That's what you've got to find. One of the reasons that Spectre was so brutal, at least in the very initial early phases, was that using Spectre, you could basically get physical memory reads in certain scenarios. And physical memory reads could have data in them that depended on recent load of the system. So, for example, if you induce the system into reading a private key and then that process dies, and then you use Spectre to try to recover the contents of that key from unused physical memory, it was pretty bad news. An interesting way to think about this, someone just said on Twitch, the notorious Flip-Flop shared this wisdom, that they always thought that behaved like hard drives, that memory behaved like hard drives. When you delete a file on a drive, it doesn't go away until that space is needed for another file, right? Until it's overwritten. Memory is very similar, with the caveat that as soon as it is grabbed by another process, it gets overwritten with zeros. But until it's grabbed by another process or some other thing in the kernel that needs to use it, it's there, completely unmodified and ready to be attacked or ready to be stolen. All right. How you do that, I'll leave it up to you. Of course, you have code execution in the kernel. You can do quite a lot of stuff that's very, very effective. You can't undelete that file. You could on a normal hard drive, but not with the overlay file systems, blah, 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 that your container runs on. But you can do some cool forensics in memory to find it. All right. We'll end it here. I'm sorry I have to bail 10 minutes early, but fitting the office hours in between childcare is a little tricky. I'll see you all tomorrow. when we will launch the Toddler 2 module. Don't forget, please, don't forget to go to pwn.college, not dojo, pwn.college, scroll down to where the modules are, click on advanced exploitation, and view all these videos. That'll be awesome. Lots of very important stuff. It'll teach you quite a lot. Deadline for Toddler 12. Sorry. Deadline for Toddler 2 is not 12/12. Let's pull up a calendar. Excuse me. How do we find an easy calendar? Okay, 2021 calendar. That's not too bad. All right. So we are going to be here. Toddler 2 will launch on November 23rd. Ooh, full screen, perfect. On November 23rd. Toddler 2 will actually be due. Shit, we can't make it due during Dead Week, can we? Connor, when's the last day that we can make Toddler 2 legally due for full credit? Depends on what legal mean. My understanding is we're not supposed to have anything due the week after school ends, right? We'll figure it out, guys. We'll tell you tomorrow. Most likely, Toddler 2 will be due on the 3rd, so you'll have just over a week and a half. But we might make it due on the 12th, along with the 50% of all of the other homeworks. Probably we should make it due on the 12th, just to encourage people to actually do it. Yeah, that makes a lot more sense. Because the Toddler 2 are going to be... how about due any day? Yeah, that's another possibility. Yeah, we could make it due on the 3rd with 100% late credit until grades are due, just to avoid any sort of complaints about assigning homework on Dead Week. All right. Yeah, let's plan for that. We'll give you the exact final answer tomorrow. Don't forget, of course, you do have until 12/12 at like 11:59 p.m. To grind through all of the prior assignments. And I think given what you've been doing now, if you go back and look at, the baby ma'am level 14 that you missed, you're going to laugh. It's going to be great. All right. Awesome. Thank you all for jumping in. Hopefully this was helpful. Make sure also, if you're really stuck on the kernel, sorry to keep pulling us back into this, we added several lectures after we started. Video coming soon is now a lie. Now there's a video here. There are videos everywhere. It's all great. We talk about mitigations that tell you exactly how to solve levels where you might not be able to execute shellcode. We talk about a lot of stuff. So go take a look. And especially if you're having trouble with shellcode, take a look at this lecture and these slides. All right. Awesome. Have a good one and good luck. See you tomorrow for Toddler 2.